Since there are lawyers in the group, I probably won't talk about earthquake prediction.
At least not in Italy, right?
Not in Italy. But I will talk about early warning later in the presentation. And I'm going to give well, let me grab my pointer. I think somebody mentioned that I had something to do with this building design, and I had nothing to do with the design of the building. But I did have a lot to do with the instrumentation program that we have in this building as far as research and being able to predict building health after a major earthquake. And I'll talk a little bit about that in a few minutes. Okay, so start out with the slide credits. These are slides that I borrowed from various people and slides I've taken myself. I didn't put them on each slide, so I wanted to mention the people that I've worked with and have helped me develop some of these slides. Okay, the summary is Alaska seismicity. I'm going to talk a little bit about seismicity to just give you sort of an idea of the seismic regime that Alaska sits in and why we should be a little bit concerned. And worry is probably not the right word, but we should at least be concerned. And when we hear things about seismic risk mitigation and things like that, we should pay attention to it and perhaps support it in some ways. I'll take a look at historic damage, what happens to structures and why it happens and why it continues to happen even though we have more and more modern design techniques and better materials that we're working with, but we'll look at why we still get damages. I'll look at some current local research that's going on, not only from a free field network we have throughout Anchorage, but also from a building instrumentation that we have here in the C Street overpass and the Frontier building. And the BP building also has some seismic instrumentation in it. And then I'll look at some current approaches we're taking, especially through the, excuse me, the Geotechnical Advisory Commission and the Seismic Commission for the state of Alaska, and what we're doing to try to mitigate the risk that occurs from a major seismic event. And then I'll take a look at a little bit of safety hints. I'm not a safety expert, and you know, my main advice to people is duck and cover. The initial approach is normally to run, but you know, when you take an earthquake like Loma Prieta that lasted maybe 22 seconds and was you know, around a magnitude 7 point earthquake, you're not going to get far in 20 seconds. And so it's much safer to duck and cover. And there's been a lot of information on the internet recently about a person that says, hey, duck and cover is bad because things fail and you get crushed. That's not, I mean, things do fail and you might get crushed, but duck and cover is still the main thing that most experts will advise people to do. And then at the end, we'll have some questions, and if they're not too hard, sometimes my wife asks me questions that are pretty hard to answer, but if they're not too hard, I'll attempt to answer them. Alaska seismicity. People sort of mix up the words risk and hazard. In fact, Alaska produces this report for FEMA every few years that's called the Seismic Hazard Mitigation Report. Well, you don't mitigate the hazard, you mitigate the risk. The hazard is the expected occurrence of an event, and the risk is the consequences of that event. We can mitigate the consequence in some way, but we can't mitigate the hazard. In this particular picture, I see there's a picture of Anchorage in the early 1900s and a picture in the about 2005, 2006. The risk is substantially different between those two, yet the hazard remains. We're always going to have the potential for a major earthquake, but as the population density grows and as the construction, the buildings inventory grows, then the risk increases given the hazard. So we mitigate the risk, the hazard is going to always be there. And we will have, I can say that, you know, we're going to have a major earthquake that will affect Anchorage sometime in the future. I don't know if it's during my lifetime, but we certainly have had them in the past, and we will continue to have them in the future. And why is that? Well, this is a cartoon of the plate boundaries for the tectonic plates. And typically our major earthquakes that we worry about occur along the tectonic boundaries. For example, the Sumatra earthquake in 2004 occurred right in this area. And you notice that in certain areas we have plates that are moving apart, okay, and that's called divergent movement. We have plates that are subtending under another plate, that's called convergent movement. And then we have plates that move in a strike-slip type fashion, and that's called a transformative type plate movement. Our major earthquakes, a lot of our major damage occurs along these plate boundaries. For example, in Chile, in 1950, we had a 9.5 earthquake, and then in 2010, there was an 8.9 earthquake, almost 9 earthquake. Along this plate boundary, again, a convergent plate boundary. And as you move up into here in 1985, on the Cocos Plate, we had a major earthquake that affected Mexico City. It was about an 8.1 earthquake in 1985. And then in California, we had San Fernando in 71. We had in 1989, we had Loma Prieta. And in 1994, we had the Northridge earthquake. So there's been 3 major earthquakes that have a big effect on infrastructure and people dying. But what we find in the US earthquakes, that the number of deaths seem to be fairly limited. For example, there was none of the deaths in the California earthquakes exceeded about 65 or 70 people. We don't get the thousands that you find in some of the other areas of the world. And I'll explain why that happens in the future in a little bit. So we've been very lucky. And a lot of that is when the earthquakes occur. A lot of times they've occurred in the evening, or when there wasn't a lot of building, a lot of the buildings weren't occupied, and that has helped a lot. And of course in 1964 we had the Alaska earthquake that had a big effect on Alaska, 100 plus killed. And then in 2002 we had the Denali Fault earthquake, a 7.9 earthquake that was the largest earthquake that occurred that year. And it actually did a lot less damage than you might have expected from an earthquake of that size. And I'll talk a little bit about that in a moment. And then, of course, we had the Haiti earthquake, 250,000 people killed, about a 6.9 earthquake, not a large earthquake from Alaska's standards, but still killed a lot of people. In China in 1972, there was an earthquake that killed, it was about an 8.1 earthquake that killed 650,000 people. And back during that period of time, China was pretty closed, so you didn't really hear much about that. People don't recognize or don't remember that earthquake much. So, and then let's see what else. And we've had, of course, other, Japan in 1995, we had the Kobe earthquake. That was about a 7.0 earthquake, but it occurred right under the city. So it was very damaging, $40 billion worth of damage and about 15,000 people killed. And then we had the recent 2011 earthquake that affected the nuclear power plants. So these plate boundaries and these plates really have a detrimental effect when they start moving. Well, they're always moving, but very slowly. Okay, so these are just a picture of divergent, convergent, transformative earthquakes. This is called normal faulting. This is a strike-slip fault, and this is the type of faulting that we have at the Aleutian megathrust, which is this, where the Pacific plate is coming underneath the North American continent plate. We get major earthquakes along this boundary, and of course the 1964 earthquake occurred there. Then we have the Denali Fault, the 2002 earthquake that broke, and then we have the Castle Mountain Fault that's had some rather large earthquakes in the past, and we expect that it could generate an earthquake in the order of 6.8 to 7.5 and have a big effect on Anchorage. And then we have well, let me talk a little bit about this, about seismic gas. Notice we have, in 1964, we had a large, about 300-mile break in the Aleutian megathrust fault. 57, we had another large break, moment magnitude 9.1, and then we had an 8.7 earthquake in 1965. So we've had some big earthquakes along the Aleutian megathrust, but there's areas where we haven't had a lot of seismic activity. Those are called seismic gaps, and they're areas where there's an expectation that there could be a major seismic event along those areas. You know, one interesting thing about the 1964 earthquake, it was very large from a moment magnitude standpoint. It's the second largest earthquake ever recorded in a populated area. But the duration was very long. It was 4 to 5 minutes of strong shaking. But the ground accelerations were relatively low. They were like 0.15 G, which is a relatively low acceleration, and most buildings should be able to withstand an acceleration. One thing that worked against it, though, was, of course, the long duration of the earthquake. And this just shows again, a pictorial view of the Pacific plate going underneath the North American continent plate, and it's along this boundary where we expect large earthquakes. And then we see this fault mapping. The Seismic Commission just completed a study on quaternary fault identification in Alaska, and there's a report on our website. And I'll talk about our website in a little bit. But these are all the faults, both active and inactive, that sort of have been faults and folds that have been identified through various studies in the past. And there's continuing studies that are going on to identify faults within Alaska, especially with the gas pipeline along that corridor. There's a lot of fault mapping. And there's some new potentially active faults that have been discovered through that mapping, or through those studies. This just shows the earthquakes in the month of October, 2,500, 2,600 earthquakes. We get 2,500 or so a month, 25 to 26,000 a year of various magnitudes. And then this one just shows the week from November 12th to the 18th, 614 events, and none of them were very big, probably in the order of a magnitude 3 or 4, which wouldn't have a big effect on built environment. Okay, this is the break in the 1964 earthquake, and this is the uplift area, and this is the subsidence area. So we had about 30 feet of uplift and up to 10 feet of subsidence. And of course, when we get an uplift like that in the water, that creates a tsunami. We can't get a tsunami from a strike-slip type faulting. So California, along the San Andreas, with the strike-slip faulting, you're not going to generate tsunami waves, but with the dip-slip or normal faulting type motion, you'll generate huge tsunami waves. And we have, Kodiak is down in here. This thing is about 300 feet long. And if we look here, this is about 6 feet of subsidence along Turning an Arm near Girdwood. And then this is probably about 12 feet or 10 feet of uplift at Montague Island. There were parts of the island uplifted more than 20 feet. So that was a big earthquake. Okay, the 2002 Denali Fault earthquake. I wanted to point this out because in October 23rd, we had a 6.7 earthquake that occurred right in this area. We had some seismic instrumentation that we were going to put in Fairbanks, the city of Fairbanks, and it hadn't been put out yet, so we rushed to the Denali Fault and put about 8 instruments along the fault right after this earthquake occurred. And November 3rd, a week or so afterwards, we had the 7.9 Denali Fault earthquake. So we were lucky to have instrumentation along that fault line that was pretty good for us. Okay, and what did that show us? This is the Denali Fault. The red area is extreme, very heavy shaking, okay? Here's the Trans-Alaska Pipeline. The engineers and geologists were very good about locating the area where the Denali Fault was crossing the pipeline corridor. And so they designated an area that we had to worry about, and they placed the pipe on the ground on sliders in that particular area. And so what happened when the Denali Fault earthquake occurred, of course, this moved substantially along these sliders. But recognize one thing, because of the directivity of this particular earthquake and the what's the word? I can't think of the word. Anyway, the major part of the of the energy was focused away from the pipe. So if this thing had been right there, we might have seen a different result from the pipe in that area. But because of directivity effects, a lot of the energy was focused away from the pipe. It still was a engineering feat to identify the area and have that pipe survive the 7.9 earthquake. Yeah.
Directivity that you're talking about, a consequence of the curvature of the structure at that point?
No. Well, as far as the curvature of the fault itself, yeah.
Oh, okay.
Yeah, that's true. Okay, I wanted to talk about, we talk about seismic waves, and you hear P wave, about P waves and S waves and things of that nature. This is an example of a P wave, and you notice the direction of the P wave, it's like a slinky moving back and forth like this. It's the fastest wave as far as the seismic waves are concerned. It arrives first, that's why it's called the primary wave. Has very little damage, it causes very little damage. It moves through solids and liquids both without any decrease in energy. And then what follows that is the secondary wave, and you see how the secondary wave has this up and down type motion. That's a very damaging wave. It's affected by liquefied soils and doesn't move quite as fast. It doesn't move through liquids itself and slows down in liquefied soils. But this is where we get a lot of our damage. And then we have surface waves that are called Rayleigh waves. Again, they're a wave that's a very damaging wave. And then finally we have what are called love waves that again are damaged. So the secondary wave, the love wave, and the Rayleigh wave are very damaging to structures and infrastructure that they move through. Okay? Isn't this interesting? Oh, I've got to tell my lawyer joke before I forget, okay? I heard that the definition of a lawyer is someone who gets I got to read this. I just heard it this morning. I hope I didn't lose it. Oh, here it is. A lawyer is someone let's see, an attorney is a person who helps you get what's coming to him or her. Okay. No more lawyer jokes. Okay, those are the waves that you feel if you're subjected to an earthquake. Okay, how come it's not moving? There we go. Okay, I want to take a look, and I'm going to look at these two numbers. The difference in energy between a magnitude 1 and a magnitude 2 earthquake is 1,000 times. Okay? So, as you go from 1 to 2 to 3 magnitude earthquakes, then the energy that's released from that earthquake increased substantially. The Chilean earthquake in 1960 was 5,600 times the Haiti earthquake that killed 250,000 people and did billions and billions of dollars worth of damage. So energy release goes up quite substantially. Okay, there's been an attempt to look at the clustering of earthquakes and to find great earthquakes as earthquakes that are magnitude 8 and below, and then giant earthquakes are magnitude 9 and above. And when they put these in a pictorial view like this, you see a clustering over a 20-year period from 50 to 70 of these giant earthquakes that you see here, okay, and great earthquakes that you see here. And then there's a 30-year hiatus, and then you start getting these big earthquakes again. And so there's research going on the clustering of giant and big earthquakes. And something that shows this a little better is this is looking at cumulative moment magnitude for various earthquakes. This is like Kamchatka, which was about an 8.9 earthquake in 1950. And then we have the Chilean earthquake in 1960, the Alaska earthquake in 1964. This is Sumatra, and this is the latest Chile earthquake. So this is just the cumulative moment magnitude and you see how much these big earthquakes affect that cumulative moment through time. Probably didn't make much sense, but that's okay. Okay, let's look at historic damage and what happens. I wanted to point out something. This is just a cartoon of two different earthquakes. 1940 Imperial Valley earthquake was in relatively stiff soils, and you see that the predominant earthquake in those stiff soils was about 0.5 to 1 G, which means that the soils were relatively stiff, and you get the maximum acceleration for these stiff soils at the low end of the period scale. In the Mexico City earthquake, it had very soft soils, and the predominant period was in the high period range, so, say 3 seconds. And what does that mean? Well, that means that this earthquake affected very short buildings that were stiff and short. This earthquake affected the medium-rise to high-rise buildings. So the point is we have to worry as structural engineers, we have to look at the frequency of the soil versus the frequency of the building and make sure that those two frequencies don't coincide. Because if they do, you get what's called resonance, and that resonance you get what's called infinite deflection. So you want to make sure that the building frequency is separated substantially from the ground frequency when you design buildings. Okay, a few things we worry about in earthquake design are ground shaking, ground rupture, ground failure, and tsunami. And then there's secondary effects, and we'll talk a little bit about each. In ground shaking, these are examples of ground shaking failures. And this is 1964 earthquake, and this was the Four Seasons Apartments. And this failed simply from shaking. Codes don't handle ground failure, and they don't address tsunami damage. What they really address is design for ground shaking itself. And as engineers, we can design buildings that will withstand most earthquakes that we could think of with proper detailing and design from ground shaking. But as a structural engineer, I have to assume that the ground is going to stay under the building after the earthquake occurs. If I can't make that logical assumption, I shouldn't be building there. And so ground failure, ground rupture are real problems with design. And of course, tsunami is another problem. So we as engineers can probably make better progress if we really get on the forefront of siting of structures and make sure that structures are sited in the proper area rather than trying to do a lot of changes in design and things of that nature. I mean, we need those changes in design, and we make those all the time, but siting of structures, especially in Anchorage, is very important. This was a design failure, and I've given 3 and 4 hour lectures on why this failed. I won't do that now. Again, this is a shaking failure. The Hill Street Apartments, unreinforced concrete masonry. City limits was 16th Avenue. They built the building right on the other side of 16th Avenue, so they didn't have to obey any codes. We had a seismic code in 1950 in Anchorage. This was unreinforced masonry. This failure led to code changes which said that you had to have a minimal amount of horizontal and vertical reinforcing in CMU construction, a minimal amount or more if design indicated. This is the Inlet Towers apartment, and this is classic shear cracking and classic shear cracking along the base of the tall shear walls. Those walls were gun-ided and painted over, and the building is, of course, now still occupied. But you don't know what's happened to the reinforcing steel. Once you have shear failures like this and strong shaking for 3 or 4 minutes, that steel that's inside there could have exceeded its tensile strength and not be, the strength that you anticipated during the design.
Break out on that? It looks like they're gone.
Here? Well, quite a few of them did. There's still some in there, but quite a few of them did. And then this is West High. It was a 2-story non-ductile concrete frame building. Prior to 1976, engineers didn't understand ductility in concrete, the ability to withstand inelastic strain without fracture, the ability to bend without breaking. And so the reinforcing at beam to column connections was not right. you have to have enough reinforcing and shear reinforcing and vertical reinforcing in these beam to column connections to make sure that they act in a ductile manner and that you don't see failures like this. So this building became a one-story building instead of a two-story building. That's where I graduated from. And this, Penny's, of course, everybody has seen this, and this again was the design era. You had major shear walls in an L shape like this, and then, you know, sort of non-shear wall type other walls, and it put a torsion effect into this building that was unanticipated, which meant that instead of having just forces like this in whatever direction, you had forces like this, but you had a twisting that wasn't anticipated in the design. That led to an automatic 5% consideration for torsion in any building that's designed, and then you do calculations to determine whether that percentage should be increased. Well, this is ground rupture. Again, we shouldn't build in areas where we expect ground rupture. This is 1964. This is Denali. This is one of the few pictures I've ever seen of a fault break across the glacier, and that's the Denali earthquake 2002. And this is, unfortunately, the house was built right on the Denali fault. That was bad. Yeah, it's in good, actually, from the Denali earthquake was the first earthquake that we've sent out teams since 1964 in Alaska. And we actually had damage assessment teams that go out and that went out and looked at damage. And the damage, you know, roadways, there were some roadways that were damaged pretty bad. There was, Northway Airport was damaged. But in general, the buildings withstood pretty well. You know, some of them were on, you know, weren't even connected to the ground. It was sort of like really crude basic isolation. I mean, you know, the ground shook and the building just rolled on these timbers that they were sitting on, so worked out pretty well. Okay, ground failure. Here's, whoops, this is Black Rapids Glacier after the Denali earthquake. Here, massive landsliding. This is, of course, a Government Hill slide after the 1964 earthquake, and that wasn't shaking damage. I think if that hadn't have failed, there probably would have been some major shaking damage too, but it was primarily ground failure that split that school in half. And this is the Turnagain area and the 4th Avenue area. And so if you're building in areas like this, then you're gonna have a problem. And there's quite a few places in Anchorage that, but I'm not making predictions, that could be a problem. And tsunami is another problem. And tsunami is a problem that you can't, well, for major structures, you can't really design for. I mean, you shouldn't locate structures in areas where you have a suspected tsunami damage. This is Seward after the 1964 earthquake. And remember, I said you shouldn't locate structures in areas where you have suspected tsunami problem. Of course, the Sea Life Center is right in this area here. And this is Kodiak, and this is Whittier. The tsunami damage from Seward came not only from the tectonic sea wave that came in, but also from massive undersea sliding close to the city itself. So it was a combination of the two that produced the tsunami wave that did substantial damage there. And then we have secondary effects. This is the Northridge earthquake in 1994. We have a gas main break, a water main break, and so that's, you know, pretty substantial. 1964 fuel tank damage. So, you know, you got to worry about design for that. And then fires at Valdez. This is Spitak, Soviet Armenia. That was an earthquake that occurred in 1988 in Soviet Armenia. There were about 25,000 people killed. But the reason I point that out is this is the type of gridlock that can occur after a major earthquake. And here we have a fire truck trying to get to the damaged area, and it's stalled in this gridlock of traffic. And that's the problem you're gonna have if you ever, well, I'm not predicting now, but if earthquake prediction ever came into vogue, and I don't think it ever will, what are you gonna do if you tell LA you're gonna have an earthquake in 72 hours? I mean, you know, you'd have a gridlock like you couldn't believe. So it's going to create other problems that are that you really have to anticipate. Oh, same picture. This picture is, and again, I'm going outside of Alaska when I show some of these. I've shown this one. This is Loma Prieta, and it's not shaking damage, but it's certainly, with this type of structure, it certainly could be shaking damage, but it's actually ground failure. This is shaking damage that occurred when you have a soft story with garages below with major living quarters above. The earthquake load is directed towards a more stiff structure, and if the soft story down below isn't properly reinforced, we see this damage all the time. And this is a parking garage at Northridge after the Northridge earthquake in 1994. That sort of imploded, actually. But the columns are acting ductily. That's a ductile failure of that column. It's not a brittle failure where the entire building collapsed on itself. It's still not what you like to see as a designer. And then we have Mexico City. This is one of the first indications I've ever seen of a steel structure with a massive failure like this. This is Kobe, Japan, after the 1994 earthquake. What's really interesting is the 1994 earthquake in Kobe, Japan occurred almost to the minute 1 year after the 1995 earthquake in Kobe occurred almost to the minute after the 1994 earthquake in Northridge. It doesn't have any correlation, but it did happen that way. I look at this guy as the world's supreme optimist, or he hasn't heard of the concept of aftershock. An aftershock after an earthquake the initial aftershocks can be of an order of 1 magnitude, maybe less than the main shock. So you can get some hellacious aftershocks after a major earthquake. So you really need to worry about that when you reoccupied structures. This is Spitak, Soviet Armenia, and this was a schoolhouse, and there were several hundred kids killed in this particular building. Lousy design, lousy construction materials. Similar here. This is an interesting, this is Nagata, Japan in 1964. It occurred the same year as the Alaska earthquake, but didn't receive a lot of notoriety, but it showed liquefaction, what liquefaction can do to buildings. In this particular building, when the soil liquefied, it tipped over on its side, but it remained intact. And the story is there was a woman hanging clothes up on the roof of this building, and as it tipped very slowly, and she sort of and walked out, went down the road, and uninjured. This particular earthquake and the Alaska earthquake led to a lot of research and new approaches to liquefied soils and how to approach them. Okay, current local research. Is this okay? Is everybody bored? No. Oh, okay, good. Okay, everybody has seen the seismically induced ground failure susceptibility map from Anchorage. This was produced in 1979, and it showed areas where you could have very high ground failure susceptibility down to very low, from the bluffs to the mountains. And this has been used through the years for various things. You know, people say, oh, I live right there, so I'm okay, which isn't true. But anyway, so this has been used. It's been modified recently, but we're not going to put out the modifications at this particular point. And the city is also looking at some changes where they provide some restrictions on heights of buildings in the downtown area where the ground failure susceptibility is in the 4 to 5 range. So that's being reviewed right now and is not open for publication at this particular point. And then we have our free field instrumentation program in Anchorage. There's 42 instruments throughout the city. The black are Alaska Science and Technology Foundation funded instruments when we had that. And the orange boxes are USGS funded instrumentation. There's 42 free field instrumentations. They're called K2 seismographs that gives us vertical and horizontal in the X and Y direction accelerations. So each of these gives us a vertical and horizontal acceleration at each of these points. So we can look at the incoming seismic wave as it comes to anchorage. And let me see if I can do this without screwing up. I'm not using my glasses, so. Oh, there we go. Okay, now I got to escape. And then this is not, excuse me, this will just take a second. No, I just want to, hit this thing. Up. Open. Okay, I'm not going to make that any bigger. Okay, this just shows you some of those instruments going off with a small earthquake that's coming across. And as the colors get brighter and brighter, the accelerations are higher and higher. Anyway, we look at this stuff, and we're real interested in ground accelerations and how the accelerations increase or decrease depending on where you are in anchorage, because that can affect how we design certain things in certain parts of the city. Okay, so that's that one. Now I got to get back. I think I can do it all by myself. Go up here and go to there, and whoop. And I go to there. Well, I don't know what I'm doing. I want to get back to my, let me just do this. Whoop. Sorry, from current slide. Okay, so we have this free field instrumentation program that's throughout the city here. We also have 6 downhole instruments at Delaney Park, and if you look out, which way is 9th Avenue, that way? There's a fenced area right on 9th Avenue, and there's 6 downhole instruments that are called hypocenters that have 3 degree of freedom accelerometers in them, and they're down to 50-foot intervals, down to 200 feet, down to the glacial till interface, which is right here. So we have, at various locations, we have these 6 accelerometer hypocenters located. So we can look at an incoming seismic wave as it passes through this particular area. And then we go to this building here, and we have seismographs. Well, actually, we have one seismograph in the basement with a 3 degree of freedom system in it. We have one at the 18th floor, and these others are accelerometers with noting accelerations in the direction you see these arrows going. So each of these arrows is an accelerometer. And so what we can do is we can look at the translatory motion of the building. We can look at torsion of the building. We can look at interstory drift, and we can look at foundation rocking by examining the accelerations in this building from here. So now, what do we do from there? We go and we go here, and I put my glasses back on, and I say escape, and then I go down here, and I hit this, and I say open, and I'm going to make this bigger. Okay, this is a single degree, a first degree of freedom motion of this particular building, and I want to point out a couple of things here. Let's see. Play again. If you look at the building, you see motion that's this way, but you also see a twisting motion. So this building, if it were perfectly symmetrical, the earthquake motions would be this way or this way in the X and Y, X direction or the Y direction. But because there's, as far as the seismic resistance is concerned, there's some non-symmetry to it. You see this torsion of the building. And look at, as I say, look at the twisting in addition to the translatory motion. And so in the Penny's department garage, and this is exaggerated motion, by the way, but in the Penny's parking garage, that twisting, that torsional motion was huge, and that's what really destroyed the building. Okay. I wanted to do, I think, this, and then I want to go to here, and I want to go to there. Okay. I'm not going to say anything about prediction, but I wanted to talk something about early warning. This is an instrumentation in California. You know, they have so much instrumentation on some of these faults, it's probably pretty hard for them to break, but there's a lot of instrumentation. But they can use this instrumentation to provide early warning. So if you had an earthquake that occurred in Salinas, then in about 10 seconds, this area of California would have 10 seconds of warning. This would have 20 seconds of warning. Earthquake faults break, wave moves at about 2 miles per second. And so you get out in the outlying areas, these areas would have 30 to 40 seconds of warning. So this is really called an early warning system, and it allows you time to duck and cover because you know something's coming. And so that's really where a lot of research is going on now, is in early warning. Well, I mean, at 2 miles per second, maybe that's probably 20, 40, 60 miles. So, I'm not sure exactly, but it's in that order. So they have enough instrumentation. We can't do that in Anchorage because, well, we could, because if we know an earthquake has occurred on the Aleutian megathrust, we don't know for sure and what effects it's going to have on Anchorage until it really hits Anchorage. And once it hits Anchorage at 2 miles per second, it's past the city. I mean, we don't have enough time to react and we don't have a dense enough instrumentation network throughout the state or the city to really handle that. Even though our network in the city is actually quite dense, not from an intelligence standpoint, but from a number of instruments standpoint. Oh, I wanted to point this out. The difference between West Coast people and East Coast people when it comes to earthquakes. This is sewage use. The green lines, to make it simple, the green lines are daily sewage use. So on the West Coast, a 5.4 earthquake occurred at this particular point right here, and you notice there's no change in sewage use. East Coast, a 5.5 earthquake occurs right here, and all of a sudden, nobody's using the bathrooms because they're all running outside. Anyway, it's called sewer sociology. Okay, current approaches. We have Alaska Seismic Hazard Safety Commission. Implementation strategies are in new construction, stop increasing the risk, don't build on bluff areas. Existing structures, if there's structures that you know are seismically unsafe, there's ways of retrofitting and strengthening them. There's things you can do from a mitigation standpoint in a lot of areas to decrease the risk. And then prepare for the consequences once you've done everything else. And the goal is seismic safety. This is our membership, and I won't go through it, everybody, for the Seismic Safety Commission, appointed by the governor. These are our powers and duties, and again, I won't go through all these because I want, maybe there's some questions at the end. I want to give some time for questions. But these are the types of things that your Seismic Safety Commission for the state is looking at. And to approach these things, we have standing committees: schools, earthquake scenario, education outreach, insurance, etc. Schools committee, we're looking at different approaches to design and construction management and construction of schools to make them safer. We have an earthquake scenario, which is a planning scenario to going on in Kodiak right now. They're looking at various parts of their infrastructure and seeing what's at risk, and then going back and doing things about infrastructure that might be at risk. Education and outreach. We sponsor a post-disaster damage assessment course for people where we train them how to go in after a major earthquake to look at buildings and document whether they're safe to reoccupy or whether they should not be occupied. And then if you look on our website, there's a website address coming up, you'll see an insurance brochure that we produced looking at the pros and cons of earthquake insurance. Our hazards identification, we just finished a report on the quaternary faulting and folding of earthquake faults in Alaska. And response and recovery is, we haven't done a lot in that area at this particular point. And then in 2014, we're having a major earthquake engineering, National Earthquake Engineering Conference that occurs every 4 years. Probably be 1,000 to 1,500 earthquake specialists in Anchorage in July of 2014, celebrating the 50th anniversary of the '64 earthquake. Okay, accomplishments of the Seismic Safety Commission. I've mentioned a lot of these. We have a task strategic plan that's been developed. And we've produced a report called the Pacific Northwest Earthquakes and Potential Effect on Alaska. We looked at what would happen if a Cascadia megathrust earthquake occurred and really wiped out the port areas in Washington and Oregon and maybe some part of California, and how that would affect goods coming into Alaska. And that report's on our particular website also. And then I've talked about the training for buildings. How do you protect yourself in an earthquake? Duck and cover. I mean, that's about all I know about earthquake safety. Yeah, that's not true, but post-earthquake safety check for injuries, of course. Gas leaks, shut off gas mains. The problem with shutting off gas mains, then the gas company has to come back in and turn it back on. So, you know, if you don't have any damage, I wouldn't rush out and shut off your gas main. Approach chimneys with caution. A lot of times we see fires where chimneys have separated and the fireboxes have separated from a house during an earthquake, and then people go in and their power is out, so they light a fire in the fireplace and burn the house down. So you got to worry about things like that. If you see damage to the electric wire, shut off the power. And then, as I mentioned, the aftershock after a big earthquake could be a 1 magnitude or more, less than the original shock. So you can have failures, massive failures of buildings that occur after aftershock. Prepare for the earthquake, and you know, I feel sort of I feel sort of odd presenting this stuff because I haven't done it. And anyway, an earthquake plan, actually it's a good idea to do something, especially if you have children at home, you have an earthquake plan and hold drills and know what you will do after a major earthquake occurs. Because, you know, predictive wise, we've had a magnitude 8 earthquake in Alaska typically every 13 years. And several of those in the past have affected Anchorage, 1957, 1952, 64. So, you know, I believe in sometime in the future there will be another major earthquake that has an effect on Anchorage. So it's good to plan for stuff like this. And this is what our company does. I've noted these backpacks that have been filled with this stuff. And this is the website where you can look that stuff up. But in each of our break rooms and each of our break rooms, we have 6 to 8 of these backpacks that are stored. So in the case of an emergency, one of these backpacks will handle 4 people for 3 days. And this particular company will develop the backpack and put anything you want in it. These cost about $120 a piece. And I think they were on sale just recently for like $106. Anyway, it's not a bad idea for building owners or even homeowners to do something like this. And this, you know, just is what you might put in. It's similar to what's in that other list. Okay, I'm just talking about, this is tsunami. I mean, if you're in a coastal area and you feel an earthquake, run like hell to the highest point you can get to because you don't know what's going to happen. Don't go back and look at it like they did in Crescent City, California after the '64 earthquake. Get to higher ground. And these are just some safety rules. If you can't get to higher ground, find a substantial building where you can get up. But you know, in Japan, that didn't work. There were a couple of 2 to 3 to 4 story buildings where the seismic wave exceeded the height of the building and still took the people out. So it's best just to stay away from those areas. Deep water, I mean, everybody knows that a seismic wave moves about the speed of a jet airplane, and then it slows down substantially when it gets into shallow water and the wave is more focused. That's all I have. Yes? No. I had to talk fast. That's not everything I could say.
Is Anchorage, would it be subject to a tsunami? And if so, has there ever been a study of how far inland?
You know, that's been a major problem because when the Tsunami Warning Center puts out a tsunami warning, it hits the televisions in Anchorage, and the thought right now is that you're not going to get a major tsunami wave in Anchorage. The Cook Inlet's too shallow, and you know, wherever the wave might start, it's going to be damped out by the time it gets to Anchorage. So there's really no danger from there's probably, that's a prediction, I'm not going to say anything. Yes?
There's a major national flood insurance program, but there's no earthquake insurance program by the federal government. Is your committee looking into that discrimination?
You know, well, no, California, after the Loma Prieta earthquake and Northridge earthquake, came up with a California insurance program that you know, aids people who want to get insurance. The problem with Alaska is the problem we have with everything. When it comes to research, when it comes to getting money for everything, we don't have enough people. And so we don't have enough people to form a group that could handle, you know, insurance claims after a major earthquake. And so you think, well, maybe you could group with somebody else. And we're taking a look at things like that.
It's really expensive, and it's like a $50,000 deductible for a home.
Yeah, I'm not sure how the deductible is reached, but yeah, it is expensive, and you know, most people don't have it, and you know, that's unfortunate. But we are looking at stuff like that, trying to. We have an insurance person on the commission, and that's one of the things that we continue to look at. And right now, we've just developed the pros and cons, so it gives people an idea why it's good to have it, and why maybe, you know, some people won't want it, type of thing. So there's
The one slide you showed of the grouping of the clustering in time
Right.
of the major earthquakes, and on the most recent one, I guess the period that we're in, there was at the top a Cascadia question mark. Is there a message there?
Well, whoever made that clustering, you know, pointed out that there is a potential for a major earthquake, a major earthquake on the Cascadia megathrust, and it could be the location for the next giant earthquake. But I'm not predicting.
Yeah, has your group provided any oversight in the port construction? I mean, just general input?
Well, no, we haven't. The Seismic Commission hasn't, but the Geotechnical Advisory Commission has. In fact, right now, I'm on the Geotechnical Advisory Commission also, and we're reviewing C.H. Tom Hill's report on that facility right now. Our stuff is due out the 20th of December, our review of the report. So the Advisory Commission is looking at it. Yeah.
I just wondered, when you said the thing that comes over the television set, the warning, is there like a civil defense siren system in Anchorage that goes off? Because there was a disaster, you know, there was a tsunami warning.
Yeah, there isn't. There are, on some of these smaller communities in Alaska that, you know, there's communities in Alaska where a tsunami, they'd have seconds to react if a major tsunami occurred. So there's coastal cities in Alaska that do have tsunami warning, you know, big sirens that go off when the warning center sets them off. Yeah.
Yeah, when I was a kid
Here?
Yeah, here it is.
I don't remember that. I probably thought it was lunch call.
Was that a liquefaction issue with all the houses that collapsed in the Turnigan neighborhood?
No, that was ground failure. That was more like bluff failure as opposed to liquefaction.
So what happens in the next big one with the next row from where it collapsed back?
Well, that's sort
The same ground conditions?
That's sort of prediction, but there's some indication that initial failure has provided some buttressing for failure, but you know, there's always a potential for, given the right earthquake, the right magnitude, the right duration, to have bluff failures. Where if you have bluffs in Anchorage, and recognize that the bluff in Turnigan failed 2 minutes into the earthquake. So you had 2 minutes of strong shaking before that bluff let go. That's a long earthquake. I mean, Loma Prieta was like 22 seconds, Kobe was 18 seconds, you know, Chile was 28 seconds. And so you get, when you talk about minutes of strong ground shaking, you're going to have a lot different effects than you would with 28 seconds or 30 seconds of ground shaking.
And after the earthquake, we were told that nobody would ever build on that land again, and now there's all these beautiful homes on it.
Well,
Deal with that.
there's a thing called structural Darwinism, and yeah, and the Geotech Advisory Commission, the Anchorage Geotechnical Advisory Commission, really fought reconstruction in those areas, but and we've recommended that they put a note on the plats that signified that this was an area that had failed in the past and had the potential for failing in the future. And I don't know if they've ever done that or not. Yeah.
You noted several times that the duration of the seismicity during the '64 earthquake was particularly long, and is that a product of the sheer area that moved?
Yeah,
So, and the length and depth, if you will.
that's exactly right.
Okay.
But, you know, the 9.5 earthquake, well, I mean, it's the same situation. The Chilean 9.5 earthquake in 1960 broke 900 miles. That's the longest break they've ever seen in a major fault area in a major earthquake. But it was 9.5 earthquake too. You know, and the Denali fault earthquake was 7.9, and it probably couldn't, that fault system probably couldn't generate much larger than that, because, you know, you start breaking the fault, and if you wanted to generate a magnitude 9 earthquake on the Denali fault, you'd be over in Russia someplace with the, you know, it'd have to be a really long break on that particular earthquake, the fault system. Yeah.
How would you relate our building codes here in Anchorage structurally, for structural engineering purposes today, in terms of how they're accommodating this risk?
Every 3 years the codes change, and you know, and Anchorage subscribes to the newest codes. It takes them time, you know, a year or so, to go through it and make their amendments and things, but they've certainly improved over time. But the problem with codes is codes are a minimal standard, and because of competition in building design and building structures and things, that minimum standard sometimes becomes a maximum. And so, and that becomes a problem. And another thing is we continue to increase the base shear number, make the number that we're inputting into the building bigger and bigger, when we should be paying more attention to the detailing, how we connect things together and how we make structure redundant, so if something fails, loads are directed to some other area to keep major collapses from occurring. Because every earthquake we see, it doesn't matter whether it's in the United States or worldwide, we see major collapses of so-called modern structures. And that typically is a design error or a construction error or material flaw. Except in Northridge, what they found out is the beam-to-column connections prescribed by code were a welded connection, beam-to-column welded connection. They found in Northridge there were some buildings being constructed that had no skin on them yet, and they saw brittle failures of these beam-to-column connections. So that code prescribed connection was inadequate, and that led to a big research area to re-look at how you connect a steel beam to a column, because the stuff they were saying you should do wasn't working. And we would never have seen that without those buildings that were going up and didn't have the skins on them. And the problem is we have structures all over the country that are beam to column welded connections, and so you don't know how many have been subjected to an earthquake. Cracks maybe have been initiated, and the next big earthquake, sort of finishes the job, because you're not going to go in. Some owners have actually gone in after the Northridge earthquake, taken the skin off and checked their connections to make sure that they were okay. But in general, you're not going to do that because it's so expensive.